we'll give a few minutes for people to maybe get back on here. I don't know, it started raining and maybe it just knocked us all out. I don't know. Not sure what happened. I'll have to recombine them together somehow, I suppose. I'm not sure. What was the last thing that I didn't see when it caught up, shut down? What was the last thing that actually happened? Okay, this time. Okay. I'm going to put the link in Moodle too, just in case people go there to try and find it. Let's do that and then we'll carry on. All right, so I don't know how what really happened there, but we were working on the Y component, so we'll go back to that. I'm not sure if everybody made it back to this one or not, but it's being recorded, so it'll be there eventually if people want to go back and look at it. All right, I'm not sure how many people are in the stream right now. Oh well. I think we're probably good. All right. So we were doing the Y component. So let's just look at it from the beginning. So what we were trying to do is figure out the Y component of this 40 Newton force. And we use the sine of theta, theta being 30 degrees, the opposite side, which is the Y component side opposite the 30-degree angle. Over the hypotenuse being the 40 Newton magnitude. And then we had solved for it, and it came out to be 20. We thought it was going to be around 17, but it came out to be 20, which is close to 17. And what I was saying at that point was that since we thought it was 17 and it came out 20, that's probably a good indicator that the 20 is correct, because the 17 was just based on us, roughly drawing out our diagram sort of to scale and looking at the Y component in our picture, and it looks about half of the X component that we drew. And had we calculated the Y component and it came out to be like 5 newtons, then we'd have to go back and look and see that maybe that's not, we did something wrong. We could look into our diagram and see if we did something with our diagram incorrectly. Or we could go in and look and see if we did some of our math incorrectly. So drawing decent diagrams, you don't have to be very precise, but if they're close, then they themselves will help you know if you're calculating the right kind of numbers when you actually go put numbers to things. All right, so that assumes that we can take a force and figure out its X and Y components. Next time we'll actually do the 3 components, X, Y, and Z. It's a little bit different. Same idea, but it'll have a little bit of, obviously, a little more to it. What if we have 2 components, or 2 forces? So let's draw us a new setup here. Let's put it like this. There's our x-axis. And let's put a y-axis over here. I am almost always going to draw x horizontal and y vertically. They don't have to be horizontal and vertical. They just have to be orthogonal to each other, so a right angle between them. Sometimes it's beneficial to align one of them with with the object that you're dealing with. Maybe it's everything's aligned in one direction, and it makes sense to put the x-axis in that same direction. That's fine, and nothing wrong with that, just as long as you make the y-axis orthogonal to the x-axis. Let's try to do a 45-degree angle here, and let's make that one, I don't know, 20. Oh, got stuck on the lasso tool. All right, let's make it 20 newtons. And let's put another one here. So let's make it, let's put it on the other side, and let's make it go down. Oh, but I want it to be straight, so let's. I'm not sure why I can't erase it. I'm just kind of stuck on a not sure. All right, so now that we're back to what I wanted it to do, but I can't. We'll just erase it that way. All right, we're going to put a vector kind of going downwards in quadrant 3. I'll make it about that long so that it looks like maybe that's 10 newtons. Again, we're not specifically measuring these things, we're just getting close. Let's put some angles on there. Actually, let's use something that's not an angle this time. So last time we did an actual angle. Let's do something like this. Well, actually not on that one. We'll do it on the other one because that one's the 45-degree angle one, so it won't make much sense there. This one, let's just do 45 degrees. This one, let's do this. So if you see one of these little deals, it's basically showing you the rise and run of this vector. So let's say the rise is 2 and the run is 1, or -1 and -2, actually, I guess, if it's going downwards. So we might end up with stuff like that to show the direction. So it's not always going to be an angle measurement from the x-axis. It might be something like this. This is, remember earlier we talked about static equilibrium here? We're not doing equilibrium yet. So equilibrium means that all these forces balance one another out. Right now we're just doing force components. So these two forces, this 20 Newton and 10 Newton, don't necessarily balance each other out and create an equilibrium system. These are just two forces that are floating around in space, and we want to add them together. So one thing you can do, again, if you draw these kind of accurately, is that you could do what's called the Parallelogram Rule. And you could just go in here and... Oh, I didn't get it. There we go. We could just copy this 10 Newton force and paste it, and then put it up here. So I have moved, I've physically added these two vectors together. Here's one vector, 20 newtons going at 45 degrees above horizontal, and then I've added the 10 newton that goes in this other direction, this 1/2 or 2/1 direction, -2 over -1 direction. And I've added them together, like by really overlapping them head to tail and showing where they end up. So what this can do is this parallelogram rule can go in and give us a graphical way. If I finish the parallelogram, let's copy this guy. Oh, not that one. Maybe I need to try and highlight it. There we go. I think I got more than just it though. We'll just draw it because that'll be simpler. So there's the other part of the parallelogram. So I've made a parallelogram, a very, kind of skewed one, but it's a parallelogram. And if I take and draw a vector from the origin to that point where the other two meet, then that'll be the resultant of this parallelogram. All right. So I could get an idea of what the resultant will look like just by graphically doing it. But if I want to know a number, then let's figure out how to do a number. So let's get rid of these. Oh, that's erasing them a little bit at a time. That's okay. And let's use, even though I said it's not in equilibrium, we can still use these equations when we're not in equilibrium, just they won't equal 0. We can still add all the forces together in the x direction. They'll just equal some number. And we can add all the forces in the y direction, and they'll equal a number. If those numbers equal 0, that's when we're in equilibrium. But if they don't equal 0, then we've added the two forces together, we've combined them, but they don't add to 0, so it's not in equilibrium. After today, everything's going to be in equilibrium because we're in statics and mechanics. And so that static part of the course means that it's going to be in equilibrium. But for just figuring out how to add forces together, it may not be in equilibrium. In fact, these two are not going to be in equilibrium. All right, so let's see what they are. Let's take our equation, summation of forces in the x direction equals something. Or in this case, in equilibrium, they equal 0. And here, they equal the x component of the resultant. So when the x component of the resultant is 0, that's when we might be in static equilibrium, when all those components are 0. But this one is not going to add to that. So we need to find the x component of the 20 Newton force. So that would be that one. And we need to find the x component of the 10 Newton force. So that would be that guy. And we need to add those two things together. Oh, not y, x component. Okay, so you might can see we've kind of created two triangles in there. There's one. Here's one. There we go. And we're trying to add those two x components. Clearly, the x component for the 20 Newton force is a good bit longer than the x component for the 10 Newton force. So we definitely have a resultant that has an x component that is going to the right. I don't know what it is, but it's going to the right. Let's figure out what it is. So for this equation, we want to add the Fx of the 20 Newton force plus Fx of the 10 Newton force. So Fx of the 20 Newton force, if we do the exact same thing that we did here, that's basically this equation all over again. F of x equals cosine of 45 degrees times 20 newtons. Oh, wait. 20 newtons times the cosine of 45 degrees. And then plus, now I'm writing a plus symbol here, and this is where there are a lot of ways you can go about doing these when you want to add components together. One way is to literally use the addition, all of the force components and let the signs of the angles take care of anything that's negative. If you want to do that process, then what you need to do is you need to measure all of your angles from the positive x-axis. So the angle for this 10 Newton force, you need to measure this angle all the way around here. You'd have to figure out that angle. I typically just want to look at the thing and say that, well, that 10 Newton force definitely has a negative going in the negative x direction, so a negative x component, and just put the minus sign in the equation. It's kind of up to you, whatever is most logical to you to do. Some people want to let the equations handle all the pluses and minuses. Other people want to put the pluses and minuses in. It just neither one is going to be the way that's going to get you any points taken off or anything like that on an exam. Whichever makes the most sense to you is the one you need to do. So I'm going to put the plus and minuses in myself. So when I go to include this x component of the 10 Newton force, I'm going to write a negative sign on it. Well, we're going to put a negative sign like that. And just put the number in there. Now, this one doesn't have an angle, though. So I've got a 1 and a 2. And none of that's an angle. So I've got to figure out, well, what do I want to do with that? So there's a couple of ways you could do this. Here's one way. This little blue 1 and 2 triangle, we could finish the triangle, and we could figure out the, remember Pythagorean Theorem, a squared plus b squared equals c squared. A is maybe the 1, so 1 squared, plus b is maybe the 2 squared. C is always the hypotenuse, so it's just c squared. And I can solve this little equation. 1 plus 4 equals c squared. So therefore c equals the square root of 5. So that's that dimension right there. What I can do with that is look at what I'm doing when I write these equations. I'm saying the cosine of 30 degrees equals something, or the sine of 30, or the cosine of 45, or whatever. But up here, we wrote, oh, cosine of any angle is the adjacent side over the hypotenuse. And sine is the opposite side over the hypotenuse. I can use these numbers, the 1, 2, and the square root of 5, as the actual numbers to put in to calculate the cosine. So for instance, or the sine, or whichever I want to do, or the tangent. So if I want to figure out the x component here, I could say that, well, the x component of the 10 newtons is 1 over the square root of 5 times 10 newtons. So 1 is in the x direction. I want to know the x component. The square root of 5 is the hypotenuse. 1 over the square root of 5 would be just like adjacent over hypotenuse, right? Adjacent side, well, I've got it kind of, the way I drew it, it's kind of upside down, I guess, from the 1 and 2. So the same ratio would be, let's put it in blue. This guy, by similar triangles, those would be the same ratios, right? 1 over 2. And then the 10 newtons would be the same ratio as the square root of 5. So you could use this directly as the definition of a cosine or a sine or a tangent, whichever one you might need. So 1 over square root of 5, if I plug that in, let's go to MathCAD. 1 over square root of 5 is 0.447. If I do, well, I don't know that angle, do I? I could calculate that angle, which would be a little redundant. That's the other thing you could do. But this number, 0.447, is the cosine of whatever that angle is. So it's just the definition of it. Another thing you could do if you have the 1 and the 2 there is you could go and figure out, well, what is that angle? You know, go and do the inverse cosine or inverse, well, since you have this opposite and adjacent sides, you could do the tangent, inverse tangent of 1 over 2, figure out the angle, and then use that angle the way you've been doing it before for putting that angle into the cosine. That kind of does like a loop, you know, you figure out the angle, using the definition of what the cosine means, and then you use the angle to figure out what the cosine is. And so it's kind of you did it twice sort of thing, but that might make more sense to some people. That might be easier to follow. But you will have some homework and exam problems where instead of 45 degrees written out like we have it with the 20 Newton force, you're going to have this rise over run little piece of a triangle that is telling you the direction. So you need to develop a method to work with those, whether or not it's just figuring out what the angle is and using the angle the way you've always done it, or using it as a definition of a cosine or a sine or whatever. So if we do this, 1 over square root of 5 times 10 newtons is going to equal, it was 0.477, right? 0.447 times 10 newtons, so that's 4.47 newtons would be the x component of the 10 newton. So that would be a way to do that one. I also know that that one is going in my negative x direction. So I would have negative 4.47 newtons here. So that would be the negative. I guess we never did calculate the 20 newton cosine of 45. Let's see what that equals. 20 newtons times cosine of 45. MathCAD, we have to tell it its degrees. 14.14 newtons. Now we have to look at these and see if these make sense. It looks like, there's about a 3-to-1 ratio there. And, if I'm looking at my picture and wondering if I've drawn it correctly, it does look like I've more or less drawn it correctly. This little x component of the 10 Newton force looks like it's about a third the length of the one for the 20 Newton force. Again, are these 1s and 2s exactly right? Probably not, but they're close. And so that's all with my diagrams. That's what I'm trying to do, is prove that the math that I did looks like the picture I drew within some amount of reason. So what this does, when I do this calculation, if I do the 14.14 newtons minus the 4.47 newtons, 9.67 newtons. So R of x, Rx, the x component of the resultant of these two forces added together, equals, I've already forgotten it, 9.67. And it's positive. The positive means that the resultant x component is to the right, because I have drawn x positive when it goes to the right. That's the way I drew the thing. So that one, I could go in, let's make it green. No, we'll make it blue. So if I drew an x vector that is 9.67, then it's probably about like this. And that little guy is the x component of the resultant. Now we need the y component of the resultant. So that's going to look a similar thing. I want to write it over there. Let me move this a little bit over here somewhere so it's not quite in our way. All right, so we want to do the same thing, but now the summation of forces in the y direction equal the y component of the resultant of these two forces. So looking at them again, the dotted lines that I drew earlier, those are the y components. So this is the y component, and this one's getting really cluttery down here, but this guy is the y component for the 10 Newton. One of them is clearly longer than the other. The 20 Newton is about twice the length of the 10 Newton one. And so that's what we're expecting, is that it's going to be about twice as much, which means the y component of our resultant should be going up a little bit. All right, so let's put our numbers in here. Whoops. The y component of the 20 Newton force. And we're going through this like very slowly. Hopefully all of this stuff is like, oh yeah, I kind of remember that. Maybe you haven't done the rise over run thing. That's okay. You've got time to figure out how you're going to deal with those before you actually have to deal with them on an exam. The first exam is like after class 10, or maybe it is class 10. So you got some time to figure that out. But you've probably seen the X and Y components before, but we're going through it very slowly just in case. So what do we have? We have the 20 Newton force times the sine, since I want the Y component in this case, sine of 45 degrees. Now that's going to be the exact same number as the X because it's 45-degree angle. Also, don't get in the habit of anytime you need an X component, you just put cosine in there, because what if the angle is measured from the y-axis? Then the cosines and sines aren't always x and y, they're y and x. So don't get in the habit of cosine is always x and sine is always y, because it won't necessarily always be true. All right, so 20 Newton sine of 45, let's see what that number is. 20 newtons times sine 45 degrees. Oh, it's the same one again. So it's the same 14.14. Keep writing in different colors. I'm going to assign it a positive sign because that 20 Newton force is going upwards. It's going to the right and upwards. Both of those are my positive directions. Down and to the left are my negative directions. So the y component for the 10 Newton force is going down and to the left, so down. It gives it a negative component. And I'll do a similar thing to what I did over here. So the y component of the 10 Newton force is equal to the 2, so the opposite side over, and the 2 is the one that's in the y direction. So that's kind of obvious why I would use the 2 if I want the y component. The 2 is in the y direction on my little direction triangle. 2 over the hypotenuse of my little direction triangle, so that's the square root of 5, times the magnitude of the 10 Newton force, which is 10 newtons. So let's see what 2 over the square root of 5, it should be double. But let's type it out. 894, or 0.894, then we multiply by 10 newtons to get 8.94 newtons, but it's going down. The 10 Newton force is pushing downward, so that's a negative 8.94 newtons. We thought they'd be about 2-to-1 ratio, and we've got 9 to 14, so that's close to 2-to-1, and we didn't do any measuring or anything, so that's probably close enough to make us feel good that we're doing the right numbers. So what are these equal? 14.14 newtons minus 8.94 newtons, 5.2 newtons. So therefore Ry, it is positive, the 14 is greater than the 8.9, so, and I've already forgotten the number, 5.2 newtons. So now if I draw my little y component of this thing, 5.2 newtons, it looks like if that was 20, then it's going to be about here. Oh, kind of missed where I was aiming there. About there. So that would be Ry. And R, the actual magnitude of the resultant, is this guy. If I know the x and y component of it, I'm drawing, well, that one is the resultant. If I want to know the magnitude of the resultant, we'll come down here and actually R equals the square root, I don't know why it's messing me up here, it keeps wanting to erase stuff, of Rx squared. Wow, I might have to let it catch up. I think the computer is a little bit slow. What we're doing is applying the Pythagorean Theorem to our resultants. Rx will be A, Ry will be B, and the resultant will be C. And we'll do Rx squared plus Ry squared equals R squared once it decides to wake up. We can go ahead and put those over here in MathCAD though while it's confusing. So R is going to equal Rx squared, well actually the square root of Rx squared plus Ry squared. We just need to give it values for Rx and Ry. I'm using MathCAD. You do not have to use MathCAD for homework or anything like that. I'm just using it so you can see the numbers I'm writing clearer. Rx was equal to, we wrote it down. If we'd have been more careful about writing our numbers down instead of just kind of using it as a calculator, then we would have had it already. But Rx was this guy right here. And Ry was this one. And then R is 11 newtons, 10.979 newtons. I wonder if this has decided to cooperate yet. Maybe it has. I'm not sure. It's acting a little weird. So all we did was R, the resultant, equals square root Rx squared plus Ry squared, which is just the Pythagorean theorem. And we plugged in our values, and it ended up that R was right at 11 newtons, 10.979. So the addition of a 20 Newton force that's at a 45-degree angle and a 10 Newton force that is at whatever angle this 1/2 is 11 newtons. If that R value had come out to be 0, that would be, we're in static equilibrium. This one came out to not be 0, so this would actually be a dynamic situation. If we wanted the angle that this resultant is at, then theta is equal to inverse tangent of Ry over Rx. So we just take the y component as the opposite side, the x component as the adjacent side, and find the inverse tangent. Let's see what MathCAD says that is. So since we have Rx and Ry over here, we can do, MathCAD likes atan. So Ry over Rx. That number that MathCAD gives us will be radians. So if we want degrees, 28.3 degrees. And it is a kind of like what I drew right here. You know, if I were to measure that one with my protractor, I don't know where I set it though. Oh well, I set it down. Oh, here it is. If I were to measure that, yeah, that actually came out pretty close. The resultant on the protractor is measuring like 29 degrees. So we're pretty close. You know, if I erased them already, but when we put the head to tail, you know, actually went and tried to graphically add these together, I think they ended, I think it was right here. So I can kind of see some of it remaining there. I think it was right there. So we weren't exactly right with our drawing, but it was close. We had an idea of where that resultant was going to land. I'm not sure if I can. Well, yeah, I'll never be able to select just that area. There's too much clutter there now. But I had drawn the this vector, the 10 Newton vector, up here. I might can get close to it doing something like this. Oh, except I didn't draw a vector. And then move that. So actually, so that was where we thought it ended. We thought it ended up there, you know. So actually we're on the right angle, but our x-coordinate was a little off on our drawing, but that's okay. Actually, this x-coordinate that I drew here could be off, you know. I just kind of guesstimated that one. All right, let's see. All right, I think we have enough time to go into what if we want to do static equilibrium. So we did all of this, static equilibrium. So that is a special case of what we just did. What we just did was just generically adding two forces together. But we might want to take that same idea of adding two forces together, but impose on it the extra constraint that this body, whatever it is that we're looking at, is in static equilibrium. So when we imply, or when we enforce that constraint, then these three equations over here are true. And since we're in 2D, we only really need the x and y for now. So the x and y equations being equal to 0 can help us kind of work backwards to figure things out. So let's set up a new one. That one's way too cluttery, and it's not in equilibrium. So let's set up a new thing. One of the, you know, let's just grab a box here. Actually, let's grab a triangle. So we've got this yellow triangle here. This is some kind of weight. I don't know what kind of weight, but it's a weight. And let's say that it weighs, let's do pounds now. We haven't done pounds. So it weighs 50 pounds. We do have pound force and pound mass. We pretty much don't ever really use pound mass in this course. That's more of a chemical engineering type thing. But MathCAD does care, and there is a distinction in certain situations. So we're going to use pound force. If I don't label it, if I just write LB for pound, then it's pound force. If I specifically, for some reason, write LBM, then yes, that's pound mass. I just don't think I'm going to write that in this course. I don't know why I would. But there are two different things, pound mass and pound force, to deal with. And pound force is pretty much all you'll see in mechanics and statics, stuff like that. Pound mass really shows up more in a chemical type of process or something like that. All right, so anyway, I've got this 50-pound yellow triangle, and it is attached, a little rope, and it's attached to a ring. Okay, so there's this little metal ring, and the ring is supported by two ropes. So we'll put, oh, did my, just don't know why it sometimes it wants to try and select stuff, and I don't want it to. I want it to draw. So there's one rope, kind of going this way. Oh, it's not wanting to draw correctly. And then we've got another rope. It's coming off at a different angle. Let's make it go kind of this way. And it's still being contrary. Now, the thing with ropes, cables, chains, string, is that typically you can't really push on them, right? They only are ever in tension. Unless it's a really big cable. You know, you could apply some compressive force to a really big cable. But in general, chains and ropes and strings and all that, you can really only pull on them. So knowing that, I typically know that the force in a cable is in the same direction that the cable is going in. And so I can draw that. I'll come back and make these red once it acts right. That is the force. Let's call that cable 2. So that'll be the force in cable 2, which it's, for some reason, didn't want to draw that. And this will be the force in cable 1. And we'll fix that once it wakes up. So this is just a diagram. It's just a sketch. There's a certain type of sketch that we want to deal with called a free body diagram. And so what a free body diagram does is it takes the same picture here that we've got, and the name is free body. So it takes a body, the body of interest, whatever we want to call the body of interest. In this case, I probably want that ring to be the body of interest. And it isolates it, or it frees it from the entire world. So it's floating in space by itself. And so that's the free part of it. And then when I isolate this body, then I can replace any kind of interaction that body had with the world, because now it's out in space floating around, with a force. And so it might be that there's a cable attached to it. I've got 2 cables here. Let's see if it's acting better now. It does seem to be acting a little better now. We can draw our cables. And I can take these cables, and instead of drawing cables, I can draw forces that are in the cables. I've labeled them F cable 1 and F cable 2. We could call them F1 and F2 just to keep it simple. And let's start drawing a free body diagram. So that the steps to doing this would be that step 1 for a free body diagram, so a free body diagram, a lot of times I'm just going to write FBD for a free body diagram instead of spelling it out the whole time. Step 1 is identify the body of interest. So I'll just do ID body of interest. This could be a bunch of things that are bolted together, welded together. It could be a piece of a bigger thing. Or it could just be one element. In this case, I'm thinking one element, just the ring. So the ring is the body of interest for us. And what I want to do next is, after I've identified this body of interest, I want to sketch the body of interest. So sketch, draw, whatever you want to do. That should say sketch. It looks weird. Let's draw a little circle here. I'm going to draw it relatively large. Because one thing about drawing these diagrams is that you're using them to kind of help you solve the problem. And so if you draw them really tiny, it's going to get real cluttery, right? So like we had over here with all these lines and arrows and braces and everything, it gets cluttery. And if you draw it really small, then it's really cluttery. So don't draw it very small. Let's draw our circle. Make it a real circle. There we go. And then since it's a ring, let's do something like that. So there's our ring that is this little ring in here. So if we've identified it and sketched it. Now, there's not a wrong way to identify the body of interest. There are better and worse ones, ones that take longer to solve the problem, ones that are faster. But as long as you follow those steps, you won't have a wrong one. You'll get better at identifying what the body of interest needs to be as you do it more. So we've done that. We've done step 1. Step 2 is we need to replace all of the interactions with forces. So all these ropes that were on here, on this ring, we need to replace those ropes with the force in the rope. So step 2 is replace any interactions with forces. Now it could be that the weight of the ring, for instance, pretty small compared to everything else going on in the, the 50-pound weight it's holding up and all that. So it could be that some of these you could just ignore. I'm going to ignore how much the ring itself weighs. Sometimes you can't do that. Maybe you drew your free body diagram and you did your free body diagram as the whole thing. You did this. And you included the 50 pounds as part of the diagram. That's totally fine. But now I can't ignore the weight of the 50-pound weight there, so I have to include that as a body force. But since I'm just looking at the ring, I don't have to include the weight of the ring. I do have to include the force of these cables, though. So I'm going to go in, and I'm going to say that, well, there's one cable here that is, the tension in that thing should be 50 pounds. Again, I'm ignoring the weight of the actual rope itself. I'm just thinking the 50-pound yellow triangle is way more significant than however much that rope weighs. So I'm going to say that there's 50 pounds right here. And that is pound force. I don't know how much force is in cable 1 or cable 2, but I know that they are pulling because ropes only pull, they don't really push. So I know that there's a force, something like that. We'll call it F2. And there's a force, something like, maybe there, F1. I don't know their magnitudes, but I know they are roughly like this. Then if I extend these lines of action, I have to fudge a little bit because my drawing wasn't that great, but I have a concurrent force system. All the lines of actions for the major forces in this system all intersect at one point. So this is a concurrent force system. Okay, so that's good. That's step 2. We replaced all the stuff. We ignored the things. The weight of the ring wasn't important. Whatever wind is blowing on the ring isn't important to me. Those are really small forces compared to everything else that's going on here. So I'm ignoring those. And these are the 3 things that I think are the most important in this system. The force in cable 1, the force in cable 2, and the force in the rope that's holding up the 50-pound triangle. All right. Now, and we've kind of already done this, label knowns and unknowns. So I knew the 50-pound force, and I didn't know F1 and F2, so I gave them variable names, F1 and F2. This would probably be a good time to apply a coordinate system. So let's put our little coordinate system here and here. Again, when you have a concurrent force system, it's usually best to put the origin of your coordinate system, of your x and y axis, it's probably best to put it at the origin or that intersection point where all of the lines of actions intersect. Then finally, step 5 on our free body diagram creation list here is dimensions. So I don't have any distances, but I have angles. I have this angle, and I have this angle. Now I didn't label them. I'm going to create angles over here. I want to actually, let's get my, if I can find it. Let's see. This one is 30 degrees. So this guy is 30 degrees. And this one is 25 degrees. Okay. And what I've done here is, get this thing out of the way here, I have created a free body diagram of a sketch of a system that I had to deal with. Once you've created the free body diagram, this guy, now I can go in and actually solve equilibrium equations. So once you create the free body diagram, and again, you don't have to draw these things very well. Just try to create something that represents the physical system that you're dealing with. You don't have to get super accurate on all the details or anything. You just need to be close. So now that I've got this, apply equilibrium equations. Let's see what time it is. Oh yeah, we have time. I think we have time to actually do this, and then we'll close it down for today and do some 3D stuff next time. All right. So our equilibrium equations are up here. X and Y. We don't need the Z one because we only have 2 dimensions. So summation of forces in X direction equals 0. So any force that goes in the X direction has to be balanced by at least one other force in the X direction. Same thing in Y. And if we had Z, then Z also. All right. So let's just write these. If you're not sure which one to write first, then just pick one. And if you can't solve it, then you can write the next one. So summation of forces in the X direction equals 0. That is, the 50-pound force has no X component. It's completely vertical, only in the Y direction, so it does not enter this equation. I'm only looking for X components of forces. F1, might as well, let's start with F2. It'll make sense why in a second. F2 has an X component. We've actually done that one before. We just had a number for F2, but now we don't have a number, so we have to write it as a variable. So F2 times the cosine of 30 degrees. That is the X component of F2. Minus, because F1, I'm looking at F1 now, F1 is pointing to the left, so minus, because left, when I drew my coordinate system, this arrow here says that X is positive when it points to the right. So if it points to the left, then it's negative. So minus. Now this one is where you got to be careful. I have got it F1 times the cosine of 25 degrees. So if for some reason, here's where you could mess up. If I gave you this angle, so 165 degrees, right? No, 155 degrees. So if I gave you the 155 degree angle, and you go and you write this thing out, F2 times cosine of 30 degrees minus F1 times cosine of 155. If I did that, that's where you will get in trouble, because what is the cosine of 155 degrees? So the cosine of 25 degrees, the one I actually measured here, is 0.906. The cosine of 155 degrees is negative 0.906. So that negative sign is going to be doubled if you wrote it in here as minus F1 times the cosine of 155. So you do have to be careful about putting negative signs in. That's one reason why it's a little safer if you're not clear on when it's going to be negative and positive and all that kind of stuff. It is a little bit safer to always measure, even if the diagram doesn't show it that way, measure all of your angles from the positive x-axis, even if they're not given that way. Just go figure out what they would be. Then everything you put in here is just going to be plus, 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 and let the actual cosine of 155 or whatever it is, let that take care of the plus and minus signs. I think it's acting up again on me. Maybe not. All right. So be careful with that. I am doing minus f1 times the cosine of 25. If you use the 155, then you need to do plus f1 times the cosine of 155, because the cosine of 155 is going to introduce a negative sign itself. Let's see what this equals. Oh, I don't know what this equals. I don't know f1 or f2. So this is just an equation I can use. If you get to that point where you have an equation but you can't do anything with it, write one of your other equations. Summation of forces in the y direction equals 0. I'm going to put them in the same order. So F2 again. F2 times the sine of 30 degrees. It's pointing upwards, so that should have a positive sign. F1 is pointing upwards. Again, I'm manually controlling the plus and minuses the way I'm doing it. Sine of 25. Now in this one, the sine of 155 is a positive number, right? So sine of 25 degrees is 0.423. Sine of 155 degrees is 0.423. So they're both positive in that case, which works out. Also, though, in the y direction, I've got the 50 pounds. So minus 50 pounds. So those two are our equilibrium equations. By themselves, I can't solve them. They both have two unknowns in them. But together, I have two equations, the same two unknowns. I can simultaneously solve these for F1 and F2. So again, I'm not going to dictate the method that you use to solve them simultaneously. Whatever method works for you to solve these two. Do keep in mind on an exam, you've only got your calculator, so you do need a method that you can use your calculator with, not MathCAD or anything like that, to solve your simultaneous equations. You'll have at least, on exam 1, there will be systems of 3 simultaneous equations. I don't think you'll ever have more than a system of 3 unknowns, but you will have some that have 3 unknowns, particularly the 3D concurrent force systems. So you do have to have a method for solving a system of 3 unknowns. Here we just have 2 unknowns, so you can use whatever method you want to do. You can add these two together, or whatever you want to do to try to solve them, or you could go over to MathCAD and solve them there. But in the end, on an exam, you have to use your calculator. So you would need, most calculators are going to have some kind of simultaneous equation solver in it. You just need to know how to use it. Let's see, we're about out of time, but let's see, how could we solve these in MathCAD? One thing we could do is we could use some matrices. So I wrote these out as almost like matrix already, and let's rearrange them so that they do look like a format I could put into a set of matrices. So what I could do is let's put them in order. F1 comes before F2. So negative F1 times cosine of 25 degrees plus F2 times cosine 30 degrees equals 0. So I'm kind of rearranging them a little bit. Positive F1 times sine of 25 degrees plus F2 times sine of 30 degrees equals, I'm going to take that negative 50 here and move it to the other side of the equal sign, so it's actually 50 pounds. And what I've got when I arrange it this way is I've got a couple of things going on. I've got all the F1 variables lined up in a column. I've got all the F2 variables lined up in a column. And I've got all the residuals, all the numbers that aren't variables. You know, they're just numbers. I got them lined up in a column, and that column is on the other side of the equal sign from all the variable stuff. So this ends up being two matrices. So a matrix here full of coefficients. So that matrix would just be negative cosine of 25 degrees, cosine of 30 degrees, sine of 25 degrees, and sine of 30 degrees times F1 and F2 equals what's called the residuals, 0 and 50. And those are in pounds. So if I can create this set of matrices, I can solve for F1 and F2 as a matrix equals this guy but the inverse of it times 0 and 50. So I've got the answer matrix. Oh, no, not A. We're going to use an A. We got the solution matrix equals the coefficient matrix. We'll call that A to the -1 times the residual matrix B. So if we just put those into MathCAD, so here's my A matrix. So what is it? Negative cosine 25 degrees. The next one was cosine of 30 degrees. The next one is sine of 25. Whoops, sine of 25 degrees. And the last one was sine of 30 degrees. And I raise that to the -1 power and multiply times a little matrix that just has the 0 pound force and 50 pound force. The answer to this is F1 over F2. Well, not over, but F1 in the top spot, F2 in the bottom spot. F1 is in the top spot because I put it in the first column over here, and F2 is in the second spot because I put it in the second column. If I had a F3, it would be in the third spot if I put it in the third column. So what this says is that, oh, that's in newtons. Let's put it in pound force. 52.8 pounds of force in cable 1, 55.3 pounds of force in cable 2. That might seem weird because the triangle only weighed 50 pounds, but it's saying that there's, what, 52 pounds? Yeah, well, 53 pounds in cable 1 and 52 pounds in cable 2. Both of them have more force in them than it takes to hold the 50-pound triangle. But you have to look at the free body diagram and look at it and see that, well, only the Y components are lifting the 50 pounds. The other two are actually acting against each other. So it's only the Y component of F1 and F2 that are adding together to equal the 50 pounds. You know, we even wrote that right here. So that is 2D static equilibrium for a concurrent force system. We'll deal with non-concurrent stuff later, but that's what we would deal with for solving here. Soon, I'm not sure if you've all been added to WebWork, but I'm going to, the first WebWork assignment, as soon as I get everyone added to WebWork, then assignment number 1 will open up, and it's this kind of thing. It's this equilibrium. Some of it is this kind of thing where you're just adding forces together, maybe not in equilibrium, but you're just trying to add the force components. Some of it might even be this kind where you're just trying to figure out what is a force component, but there's a couple of problems in WebWork that will go over those things. Next time, we will do a similar thing, but in 3 dimensions. So that'll be on Monday. I'll try to combine these back together into one. I'm not really sure why the first stream went down, but it did. And so I'll try to combine them together. At least on Moodle, they're both side by side. I'm not sure what I'll do on YouTube, but in Moodle, they're side by side, so you should be able to find both of them. All right, I will see y'all on Monday.